So welcome everyone. So today we will see the basic voltage equation of synchronous machine in D2 vehicles. Okay. So the objective is to find the voltage equations of synchronous machine in D2 variables. So first we will write down voltages in ABC. Okay, so in three phase, and then we convert it into DQ variables. So three phase machine is converted to two phase machine, that is DQ machine. Okay, so let's see the two circuits of the stator. So this is phase E. This is phase E. And this is phase C. We have stator which is connected in star like this, and they are 120 degree displaced by each other. Okay, and we have a rotor. This is stator. So this is three phase AC supply. This is phase A, B, and C. Okay, so this is stator, and this is phase winding C, and this is phase winding, and this is salient pole rotor, salient pole synchronous rotor. Okay, and this is the field windings. And this is supplied by a DC voltage, that is VF, and current flowing through this field is IF. Okay, and here we have two more windings, that is KD and KQ. Okay, so these are for damper windings in D axis and it is in Q axis. Okay. So these two are damper windings. Okay, so in D axis and Q axis. So they generally damp out the oscillations caused due to the winding phenomena in synchronous machine. Okay, and they are short circuited by copper bonds. Okay, so these damper windings are short circuited by the copper bonds. So their effect is shown in D axis and Q axis. So this is direct axis along the axis of the rotor, and this is Q axis. This is orthogonal to D axis. Okay, so we have phase A, phase B, and phase C. So these are stator winding, or these are armature winding, and in rotor circuit we have field winding. Okay, so this is main field winding, and two more windings which are accounted for the damper windings along D axis and along Q axis. Okay, so the voltage equation of each three phase winding and the field winding have general form. Okay, so any field winding or armature winding, it is voltage is V, current is I, and psi is the flux linkage. So V will be equal to, this is R into I plus rate of change of the flux linkage. Okay, so this is the basic equation, EMF voltage equation for a winding. Or here we are taking d by dt as small p. So now d by dt is referred as p. Okay, so v will be equal to IR plus p into psi. Okay, so this is the resistance of the winding, and this is the flux linkage. P is di by dt, and I is current flowing through the winding. So this basic equation we will use for both voltage for phase winding and field winding. Okay, so The phase winding and the field winding have their own inductance and their mutual inductance. In the last class, we had derived the mutual inductance between field winding and armature winding, and mutual inductance between two windings, two phase windings, okay, or armature winding. Okay, so let so we have phase windings or stator windings or armature winding. They are also known as armature as A, B, C, and rotor field winding as F. Okay, so this is F for rotor field winding, and KD and damper winding is KD and KQ. KD and KQ along Q axis and along L axis. Okay. So now we draw the matrix. So flux linkage psi of three-phase winding to the field winding. So flux linkage flux linkage psi for three-phase armature winding and field winding is given by psi A, the flux linkage for phase winding A. So psi A is equal to LA into IA. Okay. So this is phase winding A, and let's suppose voltage is minus VA and this is current. Okay, so this current is flowing through this. So this is LA into IA, and this flux. So when current flows through this phase A, it has got n number of turns. So MMF of A will be equal to IA into NA. So this gives to flux phi into S. So this flux will link to phase A and phase B. So there will be mutual flux between phase A and phase B. So this will be MAB, okay, and current will be IA. Okay, so when current flow in this phase B, okay, so then this is cyclic plus minus VB, current IB. Okay, so mutual inductance between these two phases is MAB. Similarly, when we excite this voltage, this phase winding, this is plus minus VC, current IC is flowing through this winding. So this will be MAC into IC. Okay, so this is mutual inductance between phase A and phase C, and plus it also link with the armature, field winding also. Okay, so we have to take this effect also. So this will be MAF into IF. Okay, so this will be the equation of the flux linkage in winding A. Similarly, we can write for B, flux linkage in phase B. So itself inductance will be LB into IB. Okay, and for IA it will be MVA. Mutual inductance between phase B and C will be BC into IC plus MAB into IF. Similarly, phi C will be its inductance, self-inductance LC IC plus BF and CF. This will be CAIA plus MCB. Okay. So this is the equation of the flux linkage in three-phase winding, and similarly we can write for field winding also. So for field winding, this will be plus IF LF into IF, and this is AF IA BF into IB plus BF into C. Okay, so this is the voltage, this is the flux linkage in three-phase winding and that of field winding, okay, in terms of self and mutual inductance. Okay. So let this equation equation number 1. So this is equation number 1, and small a, b, c, d are for used for phases A, B, and C, and F is used for field winding. Is used for field winding. Okay. So now we can write the voltage equation for phase A. So for this, voltage equation for phase A. So VA will be equal to IA into RA plus d by dt into phi A. Okay, so you can write as IA RA plus P times psi A. Okay, so we can write like this. Now substituting the value of psi A here, so we will have so we can write here, so VA to GA will be equal to IA RA plus P, and in place of psi A, okay. Now, so yesterday we had derived the values of NAB, it is mutual inductance between phase A and B, it is mutual inductance between phase A and C, and it is mutual inductance between armature and field winding, that is stator and rotor winding. Okay. So stator to rotor mutual inductance stator mutual inductance. So we require MAB and MAC. So MAB is equal to MBA is equal to minus half LA naught G naught plus LG cos 2 theta minus 120 and MBC is equal to MCB is equal to minus half LG naught plus LG2 cos 2 theta and MCA or MAC is equal to minus half LG naught plus LG2 cos 2 theta minus 2 units. And we also know MAF, that is stator to rotor mutual inductance. So MAF is equal to M AFM into cos. Okay, so we had yesterday we had derived this stator mutual inductance or armature mutual inductance, and this is stator to rotor mutual inductance. So this is MAF is equal to MAF A cos theta. So we will substitute the values. So this is MAB and this is MAC here and MAF. So VA will be equal to IARA plus B times P is d by dt. So LAIK plus MBA is minus half LG naught plus LG2 cos 2 theta minus 120 degrees into IB plus MAC is minus half LG naught plus LG2 cos 2 theta minus 240 degrees into IC plus MAF is MAFM cos theta Okay, so that is equation number. Okay, so similarly, we can write similar equations for VAB. Okay. So for V, for phase B, VB will be equal to IB into RA plus B times. This will be MBA plus IB plus M. This will be LB IB plus MBC IC plus MBF into. Okay, like this, and we can write VC also. So VC is equal to ICRA plus B times MCA I A plus MCB I C plus LC IC plus MCF. Okay, so this is the voltage equations for phase A, phase B, and phase C. This is VA, this is VB, and VC. Okay, and you can substitute the values of like MVA. So you can find from MVA, so substitute the value of MVA, and then MC, then LB, and MCB, MCB, and then MVA. Okay, so MAF is equal to MVF is equal to MC. Here is right. Okay. So MVF will be MAF cos theta minus 120, and MCF will be equal to MFM cos theta minus 240. So, okay. So you can find the similar values like this for B and V by substituting the values of mutual stator mutual inductance and stator to rotor mutual inductance. Okay, so you can calculate the voltage equations like this. Okay. So now we can now we will convert these ABC variables into DQ variables. Okay, so these ABC bindings can be replaced by two hypothetical or imaginary windings. This is along D axis and one along Q axis. So this voltage is VD here and current is I. And here voltage is V2 and current is I. Okay, so stator winding A, B, and C can be converted into two-phase windings. Okay, so one is along this V axis. Okay, so VS, VDS for stator and VQS for stator, and they will have same number of turns. Okay, so if this has got n s number of turns, this will be also n s number of turns, and this will be also number of turns. So why we are doing this? So for our convenience. Okay, so for we are seeing this, so this is very tedious. Okay, very laborious. So if we convert this into DQ system, okay, so the things will become more easier, quite easier. Okay, so we generally convert ABC variables into DQ variables for the easier calculations. Okay, so they will give same results using this DQ variables. Okay. So we generally use this fast transformation or rotor reference frame. Okay. So V, A, B, and C. So three voltages can be converted to here it is VD, V2 and so this will be VD, V2 or VC, this will be VAB, VB and this. Okay, so we can convert this voltage VABC in three phase into these variables VB, V, DQ and Q. So VD will be equal to root 3 by 2 into cos theta VA plus cos theta minus 120 degrees VB plus cos theta minus 240 into this. Okay, and we can write also for current also similarly. So ID will be equal to, so current can also be transferred root 3 by 2 cos theta IA plus cos theta minus 120 degrees IB and plus cos theta minus 240 degrees IC. Okay, so this is VS for stator, ADS. Okay, so this is for, and this E is for rotor. Okay, and so this is this three-phase voltage is converted to two-phase voltage like this. Okay, and three-phase current IABC are converted to two-phase current ID. So you can write similarly VQS, VQS, this is for stator, and IDS switch. Okay, so this is transformation of three variables to DQ variables in stator, which is running at the speed of rotor. So this VDS and IDS, voltage induced in them is running with the speed of the rotor. Okay. So this is the transformation. So now we will for finding VD and VS VQ voltage. Okay. So we generally prefer rotor reference frame. So this is rotor reference frame. So in this, the rotor reference frame and frame is attached to the rotor. So this frame is attached to the rotor, and this rotor reference frame is rotating with the speed of the rotor. Okay, so that means omega is equal to omega r. Okay, so it is moving with omega speed, so this is equal to omega r. So reference speed of this rotor reference will be equal to omega is equal to omega and theta is equal to theta. Okay, so this theta angle between phase A and B axis is theta r. Theta is equal to theta r. So sometimes this rotor reference frame is also known as par reference frame. So now we write BD, similarly BD is equal to ID. So this voltage is VDS, current is ID, and let resistance be RD plus P into ID, and we have one rotational EMF also. Okay, so that will be VDS omega r into sin q. So this is rotational. So similarly, VQS will be equal to IQ into RA, this is saying RA, plus psi A P into psi QS. So omega is omega r minus omega r psi D. So this is also rotational EMF. Okay, so rotational EMF in D axis, and this is in Q axis. Okay, and we can write also for field. So V field is equal to, so voltage in field, voltage equation in field winding. So this is IF into RF. So this is IF into RF plus 5 into P into psi, and there will be no rotational EMF in field winding. Okay, because this field winding or rotor winding is attached to the rotor reference frame, so they are running with same speed. Okay, so therefore there will be relative motion between these two, rotor and rotor reference frame will be zero. That's why there will be no rotational EMF induced in field winding. Okay. So rotational EMF will appear in the stator DQ winding and will have rotational EMF. Okay. So this is the stator DQ, and it is for rotor. Okay. So VABC is converted to VD. This is for stator winding VAB, that is phase ABC, is converted to DQ. Okay. So So this equation is for rotor. And similarly, we can write for this damper windings also. So VKD will be equal to VIKD into, so this current is IKD flowing in the damper winding in D axis into RKD plus P into IKD plus VKQ is equal to IKQ RKQ plus P psi K. Okay. So these three equation is for the rotor circuit. Okay. So these are for damper windings. Equation in the damper windings, and this is equal to 0 as damper windings are short circuit. Okay. So these are only meant for the damping of the oscillations. Okay. So these two will be equal to, as these are short circuited. Okay. These are short circuited. So this will be equal to 0 as damper windings are short circuited, which are used to damp out the oscillations. Okay. So these two equations are for rotor side, and these two equations, and these two equations are for stator side. Okay. So the voltage VABC is converted to these two voltage VDS and VQS. Okay. So in this way we have converted into VD and VQ. So now we deal with this. First, we solve this field winding voltage equation. Then we will solve for V and V. So voltage equation. For field winding, VF is equal to IF into RF. So this is current IF and this is resistance is RF plus d by dt psi F. Okay. And value of psi F is plus linkage is equal to MAF plus linkage between phase A and field, current is IA, plus mutual inductance between field and phase B, BF IB, plus MCF IC, plus LF into. So substitute phi F here. So VF will be equal to IF into RF plus P times MAF IA plus MBF IB plus MCF IC plus LF into. Okay. And also yesterday we have derived that MAF is equal to MAF M into cos theta. MBF is equal to MAF. So this magnitude is same, is cos theta minus 120 degree. So mutual inductance between armature, that is stator and rotor, uh, its maximum as theta is equal to 0 and it is 0 as theta is equal to 90. So this the variation of this mutual inductance is follows the cosine. Okay. So MCF is equal to MAF cos theta minus 240 degrees. So substitute the values here. So VF will be equal to IF into RF plus T times MF is MAF and cos theta into IA plus MAF and cos theta minus 120 degree into IB plus MAF and cos theta minus 240 into IC plus LF into. Okay. So taking out this MAF outside, this will be MAF, this will be cos theta into IA plus cos 120 theta minus 120 into IB plus cos theta minus 240 degree into IC plus LF into. And what is this? Cos theta into IA, cos theta minus 120 into IP and cos theta minus 240 into IC. Okay, so this is the thing. It is equal to ID. Okay. So ID is equal to cos theta into IA plus cos theta minus by path transformation into this is 2 by 3 times. Okay. And cos theta minus 240 degrees into IC. Okay. So this value can be written as root 3 by 2 into ID. Okay. So this is I. So this is IA sin cos theta IA plus cos theta 120 degree into IB and cos theta minus 240 into IC. It can be written as root 3 by 2 into IB. Okay. So VF will be equal to RF into IF plus, so this will be root 3 2 times E M AF and into IB plus LF into. So VF is equal to this. And also VF is equal to RF IF plus expression into IF. Okay. So on comparing this, so IF will be equal to root 3 by 2 okay, EMAFN IB plus NF into okay. This is PI. Okay, so comparing this, you will get flux linkage in field winding is equal to this much. Okay, so similarly, we can find the values of flux linkage psi A, psi B, and psi C. Okay, using current psi A, psi B, and psi C respectively. Okay, in terms of I P, I Q. Okay, so we had converted Vs in terms of I. Similarly, we can convert this psi A, psi B, and psi C in terms of ID, IQ, and I. Okay, so the revision of this is very laborious. Okay, so let 3 by 2 MAF, this 3 by 2 MAF, and AF, and DS, and D. Okay, so this phi F will become MD into ID plus LF into. Okay. So we can write phi D, phi D, phi D, phi Q, and phi X. So phi D will be equal to ID into RA plus psi ID into RA psi D is equal to LD ID, like this. So this is LF IF, so this will be LD ID. Plus root E by 2, similarly we can derive M A F N into I F. So when psi F is there, it is ID. So when we are putting ID, so this will be IF. Okay, and then psi Q is equal to LQ IQ, and psi naught is equal to L naught. Okay, so in this manner we can do the similar derivation, and we can find the value of psi D, psi Q, and flux linkage in DQ axis. Okay. So now MD is given this much, so this can be written as psi D is equal to LD ID plus MD into IF, psi Q is equal to LQ IQ, and psi F is equal to MD ID plus LF into IF, and psi naught equal to. Okay. So now we will substitute these values in the equation for AD. V is equal to EDS ID into RA plus phi D minus omega R into Synchronous. So here, so this will be ID into RA plus P times IDS in this much. So this will be LD ID plus P times MD IL minus omega R. YQS is LQIS, LQ into. Okay, so this is VQS. Similarly, we can find VQS is equal to IQ into RA plus P psi QS minus omega R rotational voltage VDS. So this is IQ into RA plus P times psi QS is LQ IQ minus omega R YDS is LDID plus MD. This is VDS and this is VQS in terms of IQ and ID. And V naught is equal to R naught ID times L naught. This is LD. So here the calculation is quite easy as compared to when we are doing calculation in ABC variables. Okay, that's why we prefer this two-axis transformation. Okay, so here LD is equal to this LD is equal to LA plus 3 by 2 LA 3 by 2 LG naught plus LG and LQ is equal to LA 3 by 2 LG naught minus LG and L naught is equal to L. Okay. So where LD is direct axis synchronous inductance. LD is direct axis synchronous inductance. LQ is quadrature axis synchronous inductance. And M naught is zero sequence inductance. Zero sequence inductance. Okay, so these are LD, LQ and L naught. Okay. And so this is for salient pole, and for round rotor synchronous machine, LG naught is equal to 0. For round rotor synchronous machine, that is the cylindrical pole synchronous machine, LG2 is equal to 0. LG2 is equal to 0. And LS will be equal to LA plus 3 by 2 LG. So this is all about the voltage equation of synchronous machine and DQ variables. Any doubt? Okay, then thank you.